conclude my hello. Hello. Yeah. So, 1 second. Okay. So, in my conclusion part, I will highlight what and all today's talk, the main features. So, coming to the first one, what do you mean by photonics? First of all, I have seen that many of you have unaware about this particular definition itself. So I have just again I am just telling, if you are googling nowadays, the present trend is anything, if you don't get it immediately, google it. Correct. So if we see that, we will get like multiple definitions, but I can take one example, that if we can define it as a science of light, basically the photon generation, detection and manipulation through emission, transmission, and basically it deals with the complete activities related to photon. And in another way, if we see, it is basically a study that involves the use of radiant energy such as light. So one thing I can tell you, the 21st century will depend on photonics as 20th century depended on electronics. Now, many of you would have heard about RF micro region and the normal operating regions and other things. But here also, if you see the RF signals, we can normally, if you see about a L band radar, means what exactly mean is that radar is capable of operating with a frequency between 1 to 2 gigahertz. And similarly, 2 to 4 means it is in S band. So if we deal with this photonics, this also has got different bands of operation. So basically we use the last C, L and S and C and L bands. So here it is named as short, conventional and long band. So it starts from 1460 to 1625 nanometer. Now, why do we require this photonics? Do we really require this? Yes, the answer is yes, because it reduces the, if you if you are planning to implement with the photonic technologies, I can assure you that that will reduce the volume and weight. Anyway, I will discuss all these points in detail as we pass through. Okay. And anyway, you will agree with me with the second point, that is the high bandwidth. Wherever we go, we are talking, we are many times we have heard about this particular thing, high bandwidth, high bandwidth. Fiber is having high bandwidth. Even at your home also, now you may be seeing you prefer fiber links. Now the classes are going online. And if you take the present scenario, you can see that at one point of time, maybe more than two people will be working from home. So in that case, you require very high fast data rate in your network link itself. So people are going ahead with the fiber links. And similarly, it is low loss. The thing is, in the conventional, if I take a comparison, since I am from the radar background, always I have a tendency of taking an example from that background. So if we take the conventional RF cables, if we take on an average, we'll have 1 dB per meter loss, where these fiber cables are capable of providing even less than zero point 0.1 dB per kilometer. So you can imagine what is the order of the loss when we are using this fiber links itself. Now, I'm not talking in general about the photonic techniques. We can take this as a whole. So another thing is, the moment when we are having high bandwidth, we can have the huge data handling capability. And another thing is, you will also agree with me with the fact that it is more secure compared to the normal, our conventional cables, because we cannot tap it the way we tap the normal energy from the coaxial cables. The light cannot be tapped, and it is EMI, basically electromagnetic interference free solution. That is, there is no conduction media like copper or another. Light is the main media. Light is passing through a glass media. And again, high accuracy and resolution. For example, maybe when you go through the next series of slides, you will understand this. That moment I will take this point for that till that moment to explain to you. And in this case, one more thing I wanted to tell you, I always prefer two-way communication, because I don't want, especially after lunch, it is very difficult to make you all be awake after lunch session. So I request you all, wherever you are having doubts, you can either note down at the fag end of the presentation. You can ask me, no problem. I'll be very glad to answer you. Okay. So please be interactive, and no need to be a one-way communication. Okay, now coming back to photonics in defense applications, where in general, again, this courtesy is for this particular slide. I take it from internet only. That is where optic meets electronics in defense applications. So it is it can be in multi. It can be applied in multi domains. For example, we can have in electronic warfare systems, airborne systems, and we can do it, we can use this in data distribution, secure communication, sensors. Now if you see the microphotonics, can be micro means anyway, this MWP I'm going to talk in detail, so I'll keep again this topic little later. I will explain in detail. So it covers optical beamforming, then RF signal generation, filtering, antenna remoting, local oscillator local oscillator signal generation, all these things. And digital conventional ADC can be replaced with the photonic ADCs. Anyway, this topic also I have included. And wideband digitizer, optical computing, for that purpose also we can use photonic solutions. But it is not matured in India as on today, to best of my knowledge. And fiber optic links, anyway, everywhere our prime minister is also talking about this digital India, where we everywhere they want to have the communication links. So fiber optic links are widely used in this communication sector. And similarly, optical interconnect means, for example, you will agree with me that already we are using, suppose if we are making a hardware, from one board to another board, we can use the optical fiber cable. But same way, you just imagine that on board or on one chip, you will agree with me with the fact that suppose Intel and I have read some literature somewhere that even Intel and the giant manufacturers of this processors, they are going ahead, they are facing the problem with EMI. So on board, if you want to, you may be able to increase the this processor speed, but after some time it is affected limited with this EMI issues. So how to solve this? So what I came to read this particular article, where they are talking about the on the board itself or chip, while during the design of the chip itself, they are going to have very high bandwidth chip to chip communication via optical media. So all these are going to be the future um, applications of this photonics. And another thing is quantum optics. Anyway, I'm not planning to cover this quantum radar in this talk, because my talk I will be limiting only to photonics, specifically to radar application, because of the limit, because of the time limit. But you would have heard about that now, already Google, all this giants, again they have online. I don't know how many of you are aware about it. You can access your quantum computing facility by sitting at your home. There are free download, you have got the, if you create an account, you can use it for your purpose. And similarly, what I wanted to tell is, so next future is on quantum computers and secure communication. Anyway, I covered this point. And optoelectronic sensors, I'm quite sure that today morning there was a talk on biological sensors also. Dr. Preeta Sharan had handled, so you would have exposed to that particular topic, so I'm not going in detail of that. And fiber optic sensors in different areas, that is, for example, if you are having an avionics background, for we can have these sensors fitted at the different parts of an aircraft, to, and who is it can be monitored at the fag end of the aircraft itself. For example, different parameters can be monitored from different parts of the aircraft. So in a basically the smart structure, they call it a smart structure. And anyway, I told you that I'll be explaining the microphotonics in detail. Now, let us move on to, first we have seen what is photonics, and what are all the various applications of photonics in defense domain. Now we will see what do you mean by microphotonics. So again, if you see various definitions, it is defined as the study of photonic devices operating at micro frequencies and their application to micro and optical systems. So basically, it is an interdisciplinary between the RF engineering and the photonics. Okay. So what are all the advantages? Why do we require all these things? Do we really require this? Yes. The answer is yes, because these solutions can provide reduced size, weight, and low and frequency independent propagation loss in network links. As well as I will also expand this particular point. Suppose if I'm using a component, you will agree with me that because of the high bandwidth capability, previously if I'm using a mixer for one application, here because of the wide bandwidth capability, same component can be used for mixing the signals up to 18 gigahertz or Ka band. Now I'm talking about the RF band, don't get confused. L band to Ka band, I can use the same component. But in the case of RF domain, if we are going with a mixer stage, I can only, it is frequency dependent. Suppose if I want to, I cannot convert directly L band to or one baseband signal to RF frequency of higher order. It is very difficult. You may have to have two levels of up conversions. Do you agree with me? So similarly, so what I wanted to tell you is here, same component. So it will become this frequency independent architecture for a particular system design. And it is immune to electromagnetic wave and high capacity for the broadband signals. And wide range of frequency or the entire micro tens of gigahertz, or it is not limited only with the micro frequency. It can also go beyond micro frequencies with the same architecture, and we can generate even millimeter wave solutions also. So basically, we are trying to use advantages of photonics to provide functions in microsystems. Now, okay, what are all the various micro technologies? So where and all we can have this basically the marriage between the RF and the photonics. So I have categorized again. It is my own perception. Like micro, in the case of micro signal distribution, we can use it. That you will also agree with me that it need not be limited to only the communication spectrum where we are sending only the data. So we can also use the same fiber links for the transmission of RF signals also and analog signals also. So basically, we can use this for the transmission of data through for the RF signals, and we can use antenna remoting. We need not be sitting very near to the antenna. It can be the actual operational center can be far away, kilometers away. Nothing is going to happen. We can take the data away from the antenna to a faraway location, and we can monitor. And similarly, in the signal processing area, I told you that we can use for the RF to digital conversion, which is normally in the available literature. It is named as photonic ADCs and photonic beam forming. That is, as soon as you get a signal, we can convert to photonics domain and we can form the beam. And similarly, the photonic filters and the up conversion, down conversion. Anyway, I will be explaining all these things. And another thing is micro signal measurement, wherever we want to measure the frequency of a signal, or warfare receivers, radar receivers, for all these things we can use microphotonic technologies. Now, what are the specific multifunction radar requirements of present day situations? Like we always look forward for a single unit that can perform target detection, identification, tracking, and discriminating also. That is, it has got as and day by day the things are getting increased. Like recently, you would have learned you would have heard about this drone attack at different parts of India, and I don't want to comment on that. So what I'm telling is, see, if a radar can provide an image also directly, it will be better. Not only the detection of the target, we want to detect the target, then we also want to identify whether it is a friendly target or foe target, and similarly we have to track it. And similarly, if we are able to identify through image also, it will be very beneficial. What I want to underline over here is, as the days pass by, our requirements are also increasing. If a single system can provide all these things, it is going to give a immense solutions to our many problems which are existing right now. So it should have wide bandwidth. It should have waveform flexibility. That is, not only one waveform may not be satisfying our requirements. Suppose if I am playing a waveform which will detect the target up to 10 kilometers, next moment I may require up to 20 kilometers. So basically the multi-function means the waveforms should be different, and it should be able to operate in wide band and carry a frequency flexibility, because I don't want to reveal my frequency of transmission to my enemy, because they will jam my radar. I hope you know what do you mean by the jamming of a radar. If they are able to understand our frequency of transmission, they can tap it. They are not tapping, it is called some other, it is called electronic countermeasure. And they will understand that, and they will try to pump more and more energy towards us in the same frequency. So our receiver will get saturated. So all these things, so we don't play a single frequency during the transmission. Again, randomly through some order, we will, or without order, randomly we will be, without having any order, the correct nomenclature is, we will be playing different frequencies. And superior phase noise stability, I should be able to detect my target even if the target return echo is of lower amplitude. And similarly, you should be able to provide high resolution. That is, for example, you will agree with me that I don't know how many of you are totally aware about the radar engineering part. The moment when you get a very high sample rate, you can even understand, for example, the nature of the target. I can detect the target, whether it is a helicopter, whether it is a, basically we will be able to, anyway I will be coming to, I have got a photograph also, we'll be able to identify the target in a much better way. So as and when the instantaneous bandwidth is going to be more, the resolution of the radar also, range resolution also going to increase. And it should be adaptable to environment. And it also have to have very small size, that all of us will like to have everything small. Initially, even the computers, laptops were there, it was very heavy, and it was even the monitor, everything. Nowadays it is coming as a very thin, people prefer to you bring carry it in a very small size. So any equipment or anything, if you see, people used to use in a to have a small size. And not only that, I told you that if you want to sample a large input bandwidth, you should have a very high sampling rate ADC. Even if you go with undersampling, suppose if you want to sample at more than 4 gigahertz or 8 gigahertz, conventional ADCs cannot provide the solution, because it is limited by certain factors, which I'll be covering in my following slides. And again, the sensitivity and the dynamic range of this ADCs are very important, and the ENOB, effective number of bits of ADCs, are also very important. Now, again, photonic solutions in radar systems, if we go in one more level down, what happens is, uh, one second, I have to connect my, so what exactly I wanted to tell you over here is, which are all the areas we can apply this photonics in a radar system, is basically in the signal generation part, or we can use this for photonic down converter and photonic ADC applications, and for the for beamforming applications, and for the data transmission and echo signal processing. Basically what I wanted to tell you is, okay, it is repeated, basically what I meant is, get the RF signal and digitize it and further process it in a radar, and antenna remoting applications. Now in radar system, whatever I have written over there, I have put it in a pictorial way. I could get a similar picture what was there in my mind from the internet. So I have just taken this particular thing from the internet only. So you can see that we can have photonic ADCs. Then we can use this fiber leaks for massive data communication, and we can also use for photonic digital signal processor. But people have in India and abroad, many people have started the work on photonic digital signal processing. But I should, to best of my knowledge, it is not matured yet. So, and another applications what we are looking forward is for frequency generation and antenna remoting and optical beamforming. Now you will be wondering that how we can use all these applications in the photonics domain. So I will talk about all these things in detail in my coming slides. Now, going in detail, before going in detail, I also want to just highlight what are all the various photonic radar developments what is around the world. So if you see, Italy reported in 2014 with a photonic based fully digital radar. They named it as FODIR. And then Russians are coming forward with photonic radars in their sixth generation of fighter jets. It was reported in 2018 and 2019, and similarly Germany in 2019, and Chinese keep on reporting many radars in 2017, 2018, but all this have reported in some of the publications. And but one thing I wanted to tell you, I'm quite sure that all this other part of the world is already progressed with photonics radar. But if you see, except this Italy paper, all others they are just part by part only. Nobody is talking about the internal architecture. They are only just giving as photonics radar. This is a part of that piecewise meal or whatever it is you can call it. That is only they are giving, not as a full solution. And because by the time, so if you want to be at par with the other part of the world, we have to strengthen our knowledge in all these areas, and we should develop this kind of radars. And if you see in US also, I have seen many places in many of the patent applications, US patent applications, they are given say RF signal generation, then beamforming, but they are not given the architecture. Nowhere no where they are mentioning as a full-fledged radar system where with a picture is put. So so I also came to know from one of the exhibition portal that one of the army radars of US Army radars was reported with the photonics phased array radar in 2017. So I'll just show you some of the slides on this also, so that you will be in a better position to appreciate. And this is the FODIR radar system. This is a X-band radar system which is operating at 10 gigahertz, and you with a pulse width of 1 microsecond, and it is having a range resolution of 150 meter. So I hope you know what do you mean by range resolution and maximum range of detection, minimum range of detection. So these are all the other parameters. So what I wanted to highlight here is, you can see that with a single antenna and this one particular rack, the whole radar system is made. And you can, so I have also given the link of the article which shows about talks about it. It is there in Nature Photonics in 2014, the complete architecture of this particular radar. And they also have brought out some of the articles on how this radar has been used for coastal surveillance purpose, and for the air traffic control, and for the normal surveillance of air targets. So you can see that they have brought the radar with the help of a small car, and inside the car only this data processing part is kept, and the antenna is kept outside to have the coastal surveillance and for the air traffic. And this is the at the port of Livorno, no, and this is at the Pisa airport. Now, the regarding the FODIR configuration, they have mentioned that this is basically from the antenna, whatever is coming during reception, they are converting to optical domain, and by using this photonic ADCs, direct RF to baseband signal processing is happening without having conventional mixer stages. For example, those who are working in the or those who are handle radar topics during your teaching career, you will agree with me that if you get an RF signal to convert to baseband signal, you should have multiple mixer stages with the different local oscillator signals. So all these things are going to become going to increase the complexity of the total radar system. So in this case, they are using a photonic ADC to convert this from RF signal to baseband signal. And then this signal is converted to digital format and given to normal SP for processing. So in this radar system, what I could gather was from whatever antenna output is coming, they are converting to digital domain and giving to SP. Similarly, during transmit path, whatever the signal they have, the baseband signal is given to an photonic RF generator, and the output is fed before giving to the antenna. They are converting back to RF domain and giving to the antenna. So just imagine a simple rack with an antenna is the total radar system. And this is the photograph of the what is available in the open literature about the radio photonic radar in their fifth and sixth generation of fighter aircraft, and it has been reported in 2018 and 2019. And this okay this slide, I just wanted to tell you one more important thing. See, if a radar is capable of detection and tracking and identification, it also helps us to classify the target. Depending upon if I am able to get a picture like this, it is going to help me to identify what kind of a target is this. So Chinese have reported that they have used photonic based high imaging radar for categorizing the image, to obtain the image of the target itself. And they claim that they could get a range resolution of 1.3 centimeter. Little bit I will highlight on the internal architecture, so you will be in a better position to appreciate. And those who are having interest, you can please, I request you all to go through all this literatures. It will give more and more ideas to you. So I just they consecutively was or subsequently they are reporting many this thing, like it is the latest what I heard, I found was they have reported even for range resolution of 1.3 centimeter with photonic technologies. Now, how they would have achieved this? So in this case, they claim that they are able to, they are showing that even the generation part they have used, the RF signal generation is happening through photonic method. There are various types of methods are there for RF signal generation. So they are talking about something on frequency quadrupling, where if I give an LFM waveform of say, for example, I'm just telling you one example only. You assume that I'm giving 250 megahertz or 125 megahertz center frequency, and the bandwidth of each signal is 50, say. So the output of this quadrupling output will be actually 4 times. We are going to get four times the sender frequency as well as the 4 times of the bandwidth. You just imagine where we are struggling to obtain with suppose in conventional radar what we have to use, we have to use 2 levels or 3 levels of up conversions. Are you all agreeing with me? So and similarly, to get a signal with a larger bandwidth, we have to struggle. So then this part they are showing that during transmission, the signal which is generated out of photonic method is converted to electrical domain and they are feeding to the antenna. And this part they are showing that this, when the signals are received, they are using photonic techniques to generate the actual echo signal down conversion. This part will, this MSDM along with the PD will be capable of doing the down conversion, and then it is given to ADC for digitization, and further the signals are used here. But again, I will tell you, because since I have due to our own interest, I have put some effort in this domain also. There is a limitation here. Anyway, when I'll come to that part, I will explain. So here The thing is, if you are able to increase the instantaneous bandwidth operation of a radar system, you are going to get a better resolution, range resolution. You will, those who are dealing with the radar topics, you will know that it is inversely proportional. So, as and when I am able to increase the bandwidth, your range resolution is going to increase drastically. Now, I don't know how many of you have read when that Malaysian aircraft was it was reported missing, and in somewhere in March 2014, that during that time only this also this particular interaction of this radar also was happening. So they were claiming that if we would have able to if this particular radar was used during for the tracking and the other purpose, they could have immediately. So in contrast to photonics, in contrast to the conventional system, photonic systems are able to provide high precision and ultra wideband solutions, which will generate a lot of advantages for the detection purpose. Now, again, this is they were a lot of articles have popped up during that occasion. So that time, one of the thing was they are telling that we are substituting everything with electronics with photonics, and they are also reporting, those who are interested, you can please have a look on this. It's quite interesting the way they are claiming that it would have been easy to track where this particular target would have missed. And another thing, what I wanted to tell you is the latest advantages in the quantum domain also talks about that. I don't know how many of you have again come across with the quantum topics. So there also the reports says that instead of detecting a target, for example, I will take a human example itself. Don't take, this is only for analogy I am taking. If I'm able to identify, if I'm seeing a human with this kind of radars with a high resolution or quantum radars, we will be able to pinpoint the eyeball of the human being itself. Not only the detection or identification, we can also identify the parts of the human being. For if we take it in terms of the target, it is going to help us in identifying. For example, if a drone is flying, if I am able to give a image, I'll come to know whether it is a drone or some other target. Don't you agree with me? So all these are possible if we are able to give multi functions with a higher bandwidth and all other things. It is going to enhance the performance of the radar system. Now, what are all the issues faced in the current electronic domain? So today's best electronic DDCs are available only at few gigahertz. Suppose if I want to generate, for example, I will consider an example with a millimeter wave itself. If you are taking 40 gigahertz signal, suppose you assume that I want to generate a carrier of wave of 40 gigahertz. How will you generate? We have to have multiple up conversion modules and multiple LO signals for this up conversion process. Similarly, all these are majority of the cases, these mixer stages introduce the moment when you do one multiplication itself, it introduces phase noise, it adds again a lot of distortions and other things. So similarly, in the case of electronic ADCs, it works only with a few gigahertz. I think recently I found that again, those who are working with the digital domain also, there are some high speed ADCs, but it works up to only few gigahertz. Suppose if I want to give a, is it possible for me to give a RF signal directly to an ADC which is working at 40 gigahertz, directly to an ADC to sample it? Answer is no. With the conventional ADCs, it is impossible. But with the help of your photonic solutions, it is possible. So directly you can feed 40 gigahertz and get the sampled output. So even in this Fodder paper itself, they have nicely explained how it has happened. And anyway, practically also we have implemented. I can show you the results of this photonic ADC. And the moment when I am using photonic methods for this sampling process, what happens is, you will agree with me that the jitter, those who are purely working in the photonics domain, you will agree with me that this components are capable of providing jitter of the order of even few femtoseconds, where in the conventional electronic solutions may be able to give only few picoseconds. So again, the noise, when the noise is very low, we will be able to detect the target in a much precise way, even in the presence of a noise. And another thing I wanted to highlight over here is, in the case of electronics, as the frequency increases, your phase noise is going to increase. But in the case of photonics, beyond a very high value of RF frequency, your phase noise is going to be remaining same, because I told you that most of the components are having wide bandwidth of operation also. And again, frequency flexibility, reconfigurability, I'll explain this so that you will understand. Suppose if I'm using a signal photonic method for generating RF signals, say the same method can be used, same components itself can be used for the generation of the signals up to say 40 gigahertz or beyond that. But it is only, limitation is only the bandwidth of certain components. Anyway, when I'll show you the when I'll show you the block diagram, I will explain to you. And this here what happens is, concurrently I can have the, from the same output itself I can generate RF S band signal, RF X band signal, X for Xmas, RF K band signal. And only thing is, I have to give the front end antenna the output of these signals to different front end antennas. So just by varying the front end portion, you will be in a position to have multi-band frequency radars. That means, for example, if I operate in one frequency, I may not be, the radar capabilities are, say, uh, C1. So if I operate in X band, X for Xmas, its capability will be C2. So depending upon the application, I can have multi-band operational radars, and no need of up and down conversions. I already explained to you, and it supports very high wide bandwidth. So highly stable, even after 60 gigahertz also you will get very highly stable output. And agile frequency hopping. Frequency hopping means, I told you that we are not sending the signal only in single frequency. So the hopping is very easy, and multiple simultaneous carrier generation. Okay. Now let us have a look on what are all the specifications, like parameter enhancements in the whatever is happening in terms of the photonic transmitter compared to the electronic radar transmitter. So one thing is, the very important fact is, it can generate the signals up to 40 gigahertz, where in conventional radar system, if you want to generate more than 2 gigahertz, you should have up conversion modules. And not only that, each up conversion module you require LOs also, local oscillator generation modules. And similarly, signal jitter, or majority of the points I have explained, but this table summarizes all these things. So where here the signal jitter can be less than femtoseconds, where in the other case we are talking about 0.1 picoseconds at RF domain. And signal to noise ratio, if you see, both are almost comparable, and it is also having almost comparable SFDR. So if you see the advantages of, straight away this table highlights the advantages of photonics over the electronic counterpart. Now let's have a look on what are the advantages of receiver section. So in a radar, if you see again, if you want to give a signal, say, of which is operating at 40 gigahertz, before sampling, you will agree with me that you have to down convert the signal because of the limitation of the sampling frequency of the ADC. So you may require down conversion at a very, the moment when you go for very high frequencies, you require the down conversion module. But in the case of photonics, you can give direct 40 gigahertz signal at the input of a photonic ADC to get the baseband signal. And similarly, instantaneous bandwidth. Please don't confuse with what I meant by 40 gigahertz means, here it is carrier signal, and the bandwidth. if I'm using bandwidth of say 10 megahertz for a tracking of a target, in this case, this 40 paper talks about a bandwidth of 200 megahertz. But one thing I can tell you here, it is extendable. They are using MLL, mod lock laser, for the transmitter and receiver section. And you all will agree with me that even rep rates greater than or easily available up to 10 gigahertz, easily available MLLs are easily available. So that means if electronics doesn't have limitations, we can go. What I meant is, finally this sample signals are going to signal processing section. If our interfaces and signal processing is capable of getting the data at a very high rate, I can have a bandwidth up to even 10 megahertz. Sorry, not megahertz, 10 gigahertz. Then you just imagine, if we are getting a sampling rate of 10 gigahertz, obviously your range resolution is going to drastically increase. So we have seen in the Chinese literature itself. In my previous slide, I showed you that they could identify the parts of the aircraft itself. Tomorrow, if you want to detect a drone, if I'm able to identify with a small imaging facility, it will be very helpful for us to know what kind of a target it is. And similarly, spurious free dynamic range, effective number of bits, where we are here, we require even for photonics, less than 7 bits is more than sufficient for detection, up to 40 gigahertz. Where in conventional ADCs, even if we use 14 bits, you all will agree with me that 2 will be sometimes we use even 4 bits or 3 bits, but 2 is common. We will take it as the noise bits. So out of 14, only 12 will be useful. Now, I will also share with you with some of the work which we have done at our lab, and almost all the slides now. Our work, what I am presenting, is already published works only. So, of those who want in detail of this may be able to find out in the open literature. So this is how we can generate RF signal directly. That this particular slide shows the optical heterodyning method, in which we can beat two laser outputs. Later, the two laser outputs are power combined and pass through a PD photo detector, RF radio or fiber, or RF or fiber receiver. And if we can this same principle will help us to extend this to for a higher bandwidth and to obtain low phase noise signal. Anyway, with my result I will explain more. And signals with various modulation format, this particular signal generation method helps not only for carrier signal generation, we can also generate modulated signals. Any kind of modulated signal can be generated by using this. Now, again, in this particular block shows the generation by using a mod lock laser. So depending upon the carrier frequency to be generated, we have to use two different optical filters, and the output of this optical filter is given to a modulator, where one of the inputs is your baseband radar signal. So directly by just beating these two modes of model MLL, I can get the carrier frequency. This is power combined and it is given to a photo detector. We can get even the signals up to beyond millimeter wave range. For example, microwave frequency range, even 40 gigahertz, 45 gigahertz we can generate. So the same method, and if you search in the web also, those who are working in the microphotonics region, you will agree with me that there are photo detectors or RF receivers which works, a single one can operate up to some are offering up to 25 gigahertz, some are offering up to 18 gigahertz, some are offering up to say 10 gigahertz. So the same architecture can be used for the generation of RF L2, any band, LSCX, any band. Okay. So the same architecture is enough. So some simulation studies we have done it. This is just to show that 1 gigahertz signal is generated in the modeling environment, and the same output signal is we try to generate at the lab. So this is the 1 gigahertz signal. Now, The same method can be applied for the comms signal generation also by using. Again, I wanted to highlight one more point. It should be coherently working. If there is any problem, everything should be from a single source. So by using multiple laser output, we can generate the comm signals. Now, this shows the generation. This is only to show you some of the results I have just pulled out. In the case of simulation of a comm signal with a 5 gigahertz, 10 gigahertz, simultaneously you can generate by through this optical heterodyne method. Then some of you may be having some doubts in the mind that this optical heterodyning, always we talk about that there is a shift in the basically the MSDM bias and all those things, anyway, there are a lot of solutions for that. I will explain to you about how to get rid of that also. And this is the corresponding experimental result output for 5, 10 and 15 gigahertz signal generation. And another thing is with modulated signal generation, that means out of that two lasers which I showed in my previous slide, in case if I'm able to keep one laser stable and the other laser, if I'm able to program such a way that it is with respect to time, it is varying with a particular slope, lambda by t should be, lambda variation with t should be in a typical format, you will be able to generate LFM signal at the output. So this is the modeling output, and this is the corresponding experimental output. Now, this is one of the very important achievement, that is we try to implement this photonic ADC at our lab. So the principle used over here is um, one of the inputs to this optical modulator will be the actual RF signal. In a radar system, if you consider, this will be our received echo. When the signal is coming, that goes as the input to this session, and then we will be feeding this MLL pulses as sampling, optical sampling clocks, and optical sampling clock optical sampling clocks, and this will be used for sampling the received echo signal. And finally, the received echo signal can be converted to the electrical domain by using a photodiode or RF receiver. And if you see, then you will be wondering, I have written electronic ADC. I don't know how many of you are exposed to photonic ADCs. If you see, photonic ADC means in the literature, open literature itself, different types of photonic ADCs are there. The thing is, in we can do sampling in photonics domain and quantization in electronics domain, or sampling and quantization in photonics domain, and like that with different combinations. So four different types of photonic ADCs are reported. And in this approach, I have chosen where the sampling is done through optical means and the quantization is done in electrical means, so electronic means. That is the reason that this electronic ADC is there at the fag end. So if you ask me, I can give a signal of 40 gigahertz directly to these blocks. This whole block is known as photonic ADC in the open literature also. So where and this particular this blocks, for example, these two are inputs. Okay, the photonic ADC is only this much, where two inputs, one is RF and one is this ultra short pulses from a MLN. So directly I can generate the baseband. Even if I give 40 gigahertz or 10 gigahertz or 5 gigahertz, I can generate the baseband signal here. And after that, this electronic ADC is used only for converting to digital samples. So these samples are further can be taken further to the signal processing unit for further processing. So now this is the setup we have used. Don't get worried about the size of this module, because we just wanted to check the performance of this particular architecture or configuration. So we have pulled out some of the existing components which are available. So that's why each module is very, very big. When we are trying to realize the things, many of the things are available as small package form factor components. So easily we can accommodate the entire unit in a small package, a small unit. So what we have done is here, we try to give an S band signal. Now, the moment when I am talking right now, I am talking about the RF S band. S band means it operates between 2 to 4 gigahertz. So here I have chosen a signal, input signal of 2.51 gigahertz with a bandwidth of 15 megahertz with a signal level of minus 54.76. So what is happening over here is, by using the suitable mode of MLL, the down conversion, the way we are doing in the electrical domain, the down conversion will be happening, and then further it will be converted to electrical domain and then digitized. So by using, I vaguely remember that by using 99th mode, we can reduce the sender frequency to 22 megahertz. Once if it is brought down to a baseband signal, we can use it in a normal way. So the most highlighting factor is, compared to our electrical domain, this electronic domain, this photonic capabilities are going to give a very less noise, less jitter solutions to our, even our radar system too. Now, next is photonics, up conversion, up and down conversion of signal. This also I just included for you people to get an idea how here also many in many open literature it is many methods are given. But only thing is, what I found is, if I'm using this method for up and down conversion, again we are going to increase the complexity. Compared to photonic ADC, this is slightly going to increase the number of components in the up and down conversion chain. So here we can see that the way we used to mix it with a local oscillator signal previously, here the laser wavelengths are selected such a way that these signals are up converted or down converted. So by varying the selection of this laser frequencies, we can make the signal to up convert or down convert. I'm not specifically giving the values of all these things. All these are available in, we have published the many of our activities. So it is available also. So depending upon our requirement, you may have to select this laser wavelengths for up conversion and down conversion. Now, coming back to this outputs, you can say I brought out one. The laser frequencies are chosen such a way that the signal is up converted to 1 gigahertz, and in another case, laser is selected. Intermediate laser frequency is selected to reduce the frequency to 500 megahertz. So basically, I wanted to bring out that by varying the laser output frequencies, we can do either up conversion or down conversion of the signal. Now, you may be wondering that this slide you had seen before. Why do we record this slide again? I will highlight the thing. I told you that photonics supports very high bandwidth, even up to gigahertz. The moment when we are sampling, you assume a signal. For example, this is also to make you understand only I'm telling. See, you assume that you are having a signal of, for example, I'll take you take 2 gigahertz sender frequency and 250 megahertz. No, instead of 250, we'll take 500 megahertz bandwidth for this IF signal. So if I use the quadrupling method means it is called as dual parallel MSDMs, which basically configure the MSDMs in different bias points to operate either the quadruple signal, or we can get different combination output. So in the case of quadrupling, what happens is you will get the 4 time. So what will happen? Your sender frequency will now become 8 gigahertz and your bandwidth becomes 2 gigahertz. Now, if you want to use for the timing, you may have to assume that you are getting a signal which is having a very high bandwidth. which in the normal case, if we are using 10 megahertz and all, here we are getting a signal which is having more than 2 gigahertz. So this method I explained to you, but you assume that in the conventional radar system, what happens when I am trying to, let me see in the next slide, I am explaining or not. Okay, otherwise with this slide I can explain in a much better way. I told you that here when you are receiving also, you will face with the moment when you are facing receiving the signal with a wide band, that signal will face, you would have heard about this beam squint effect. Anyway, in my next slide I'll explain. So we should have something to correct that effect at the receiver stage. Otherwise, whatever signal we are receiving is affected with this error. So even this Chinese people have mentioned about it, but they never told what kind of a method they have used. So we have put effort in that direction also. So I will just highlight something on this. Those who are dealing with RF engineering side or radar topics, you will agree with me that for beam steering, or I don't know how many of you are there. So I'll explain in general the beam steering application. After that, I will tell you what is beam squint. So you assume a ULA, uniformly linear array, with n elements. Say. So what happens if you are using a phase shift beamformer for beam steering application? What will you do? You will give first element. You will give 0. Then you will give alpha phase shift. Then 2 alpha and m 1 into alpha. So where D is the element spacing. I'm considering only uniformly single linear array. But you should also imagine that in the normal radar complex system, modern radars, it is not a linear array. We will have two-dimensional, both the sides, maybe thousands, 2000, 3000, 4000 elements. So you should imagine how difficult it is. And because of this, what I wanted to tell you over here is, each time this depending upon the steering angle, that alpha is computed as 2 pi by lambda into d into sine theta, and this depending upon the angle of steering, this alpha is varying, and accordingly this phase shift should be loaded in the phase shifters which are associated with each of the elements. But the moment when you are going for wide bandwidth application, here you can see that there is a factor lambda. Lambda is nothing but a factor which is depending upon the frequency of operation. Yes, frequency of operation. So when you are having a wide bandwidth for the signal, what will happen? This lambda variation is also going to be very high. So the moment when you are going for, when I am looking at, for example, you assume that I'm looking at 30 degree with a frequency of 60. Sorry. I'm looking at 60 degree with an operating frequency of 9 gigahertz. Say. When I am seeing 9 plus some little delta f, it may not be looking in the same, even though I am putting 60, because of this problem, because there will be a squint effect. This effect is known as beam squint. But if you put, instead of phase shifting, if you are introducing time delay, which is a factor of d sine theta by c, which is independent of frequency, this squint effect can be avoided. But the method in that whatever they have reported is with a phase shifter. So they have told that we have corrected in the digital domain. So for that, what we should do, even if we get a signal like this, we should be in a position to correct after receiving the signal. So that towards that also we have done some work. Those who are new to beam squint, I've just pulled out some result on beam squint. Suppose if you assume a array of 128 element and d with an element spacing of 17.38, you can see that the moment see you can see that 9 gigahertz, it is pointing at exactly 60, that blue color. Almost maroon. I hope you are able to see this one. Okay. But the moment the frequency of operation is slightly varying to 8.8 or 9.2, there is a variation. You can see that this is called squint effect. So this cannot be permitted. We cannot allow this to happen in a radar system. We have to come out of this even with the wideband. With the photonics, we found that we can operate with at very high bandwidth. But that alone will not fetch our result. For that, what we should do, we should also find out a method. Even that's why I always tell, even if the photonics allows us many things, the final thing is your limitation on the electronics. So a combination of this should be used for the best optimized performance. That will be the best statement to give you. So here I also just wanted to show you with some if you are there is a what we have done is we try to convert the signal to frequency domain, and then we did the correction, and then after forming the beam again we have converted back to the time domain, so we found that you can see that first beamformer output was this green color. Then after that, without you can see that PC output with constant wavelength means with the beam. See, conventionally only one lambda. So with a constant lambda, if you calculate, the beam squint is happening. That is black color. You can see that all these are black beam squint effect. But the moment we corrected, you are getting the output which is happening with the original expected output. Original expected output is red in color and green also matching with this. What exactly I wanted to tell you is the moment, because of the photonics, we are able to increase the bandwidth, but that will introduce this effect if we are going with a phase shift beamformers. Okay, please don't confuse with now I explain to you. And another thing is we also tested the output with multi beamformer output. So depending upon if I'm forming the 60-degree angle, depending upon the wherever the steering angle is matching with the our beamformer weights, there you will get a peak. All other places you will get a different this thing. And this is effect of bandwidth. The moment when you see, then you will be wondering how it is working. Most of the other than imaging radars, all other radar work in the narrow band. So this effect will not be applicable in narrow band applications. So the conventional, almost all the radars other than imaging radars, okay, don't get confused again, it will operate in narrow band. So this you can see that in the narrow band the effect is not there. But the moment when you are going for imaging kind of application where we require even that also imaging, a rough idea over the target also should be there. There you will see this beam squint effect. Because of that you will see the signal gets distorted. Now, another solution to this problem is do everything in optical domain itself rather than using a combination of RF and electronics. We can also reduce, we can also do like this. How? That is, in this case, the beamforming will be done purely in photonics domain. How to do that? So again, here the output from the antenna elements are converted to optical domain when during reception, and since there are multiple channels, we can do the multiplexing of the signal, and we can send it through a single fiber to time delay network. You also I hope you remember that I had shown you one equation in which I am telling when it is time delay there is no dependency on the frequency, so there is no squint effect. So in that case, if you generate the signal and then that signal is given with proper your one second. So proper if you take the generate the signal and give the time delay according to your element position and combine this, and finally it is converted back to the RF domain after forming the beam. Okay, if you do that, it is we will this beam squint effect will not be there. And similarly during transmission, this portion is mainly for see, here it is converted to optical, and then and after that it is or I will take the transmission point itself. Suppose if you are taking this, with the help of this modulator we will generate the optical signal, and in the optical domain itself we are introducing the time delay. If the first element is having 0, The second element will have delta T, then 2 delta T, 3 delta T, and it will be N minus 1 delta T. Then finally, all these things are combined to form the beam, and the signal is converted back to RF before transmission. So the beam is steered, the basic steering is happening with all these things. Okay, so in the optical domain itself, we are introducing the time delay. Now, what are the advantages? We can use the two-time delay lines for this purpose. Dispersive fibers and a combination of tunable lasers can be used, and it eliminates bulky RF beamformers and increases the number of beams. We can do it. Nowadays, those who are working in the photonic domain, you will agree with me that you can introduce this delay very easily in the through waveguide approach. So we can increase the number of beams on a particular chip. Nowadays, the many places there are research has been reported that they are trying to make 16 element beam forming chip, then 32 element beam forming. So you will agree with me that where we are dealing with very big systems, we can minimize the total size of the chip, and we can with the help of photonic integrated ICs. Now, frequency independent wide bandwidth, I explained to you, because of the wide bandwidth capability of photonic, the same chip can be used for your input S band signal, S for ship, and even up to L, C, X, all are I am talking about RF band. Okay. And it is independent, frequency independent wide band steering is possible. So in this direction also, we try to do some things in our lab. So basically, here, with the help of this is the RF input. With the help of a modulator, we convert it to optical domain, and we try to introduce the time delay in the optical domain itself. The basic equation and all I have shown you in the previous slide, and we try to see whether the actual signal is getting delayed or not after converting back to RF domain. So we could then, what we have done is, after that we try to get a signal analyzer here, and we try to form the beam as if it is coming from 2-3 channels we used, and by using each of the delays, the output signal we used for formation of beam. So what we have done is, we try to steer the beam with 8 gigahertz signal steered at 30-degree output is shown here. 30 means here it will be 1 by 3 pi. Okay, that's why you are getting here. And another yeah, and here pi by 6, that it was pi by 6, and here it is 60-degree means it will be pi by 3. That's why it is centered at here. Now, again, another application is, so we have seen this microphotonic techniques can be used for signal generation. I told you about the carrier signal generation, then multi-band frequency generation, then modulated signal frequency generation. Then we also saw photonic ADC, photonic up and down conversion, and photonic beamformers. Now, one of another applications which I want to touch upon is how we can use in the distribution networks. Why I chose this topic last is because you have already heard from many places. You would have already heard from many places that in communication field within India itself, many places we are using this fiber networks for data communication. Even our own house, we are using this fiber communication network. C dot and all are in C dot and all, they are widely using this for the data transmission. So, but here, in our case, I am going to talk much about RF transmission rather than data. Data is very well proven in this digital domain. Everybody is using. So, in RF domain, when we are using, what are all the parameters we have to consider? So again, when we are introducing optical networks for RF communication, it provides high bandwidth. Then it helps in transmission of both RF and digital signals. And when we are trying, it need not be like in our conventional cable, RF cable. If you are having 100 signals, is it possible for you to transmit all 100 signals through a single fiber? Answer is no, because of electromagnetic interference. But in the case of RF, fiber communication, I can convert each of the RF signals into 1 lambda. And if we can pass all the lambdas through a single fiber. And this technique is called WDM, that is wavelength division multiplexing. That means I am assigning each of the RF signals to 1 lambda, and then it is multiplex and send over a single fiber. So you can use a single fiber for multiple signal carrier. And is it necessary that all should be RF? No. One can be RF, one can be your digital, one can be your control signal, one can be your synchronization signal. So what I wanted to highlight over here is the introduction of fiber for this kind of applications is going to help in a radar system drastically. So initially when we started almost 12 to 15 years back, the first thing what we were trying to do was we were trying to introduce these signals through a fiber link. And then you can see that this is a radar exciter, conventional radar exciter, where RF will be generated. It is given to a RF transmitter, and then this transmitted signal is passed through a single fiber link, and it is converted back to RF receiver, converted back to RF with the help of a RF receiver, and then it is monitored with the help of a RTSS, real time signal analyzer. So what I wanted to tell over here is, in a radar which is having more than thousands of elements, there are multiple cables. Conventionally, it was carried through with the help of multiple coaxial cables because of interference issues. And you can imagine that I cannot leave one cable just like that. There will be interference. So what we should do, we should also properly shield it. And each shielded cables are going to give complex it is going to add the weight as well as the complexity of this distribution system. So um, in this case, this outputs you need not worry, but I will try to explain. This is, you assume that I am sending from this exciter multiple pulses. Okay, so this green is actually the envelope of the actual. You assume that inside this green there are LFM signal. LFM means linear frequency modulated signal. And when I'm doing the pulse compression of that, at the fag end I will get a peak, because pulse compression is nothing but match filtering process. So this is the input and this is the output. You can see that even after passing to the fiber link, I was getting, there was no degradation in the performance of the link, and I could retrieve back the original signal. And this is the zoomed version of this PC output. So even here the main criteria is how much what is the first side lobe level occurring, and what is so you can see that it is pretty down here, so not a problem at all. And another thing is, then one more thing I wanted to introduce before we move on to a case study is there is again, those who are working in photonics domain, you would have heard about this photonic integrated circuits, that is PIC. PIC is lot of optical devices can be formed in a simple sense. Lot of optical devices can be put it in a single form of a single photonic IC, which will give small form factor. And obviously the moment it is small form factor, it is going to result in a compact solution. So like our electronic ICs, photonic ICs are also available, and different types of materials are used for this purpose. 3-5 materials and silicon material, and each has got its own pros and cons. And nowadays the most advanced thing is 3-5 materials, and I'm not going to in depth of that PICs because of the lack of time. I have just introduced this topic. Those who are interested, even nowadays microwave photonic chips are available, and many of the academic institutions and research institutions are working on the development of the same. And now quickly I will glance through a case study also within next half an hour, or if you want me to stop before 10 minutes, I can stop it, not a problem, so that I will you can interact with me for last 10 minutes. Within 20 minutes maybe, okay, I can stop it. And I will just to now till now I was telling about the various activities and tests and whatever we conducted everything. But now those who are wondering about how to realize in a radar system, so a small case study also I have brought it on WDM based radar signal distribution network. So at present, if you see, I told you that more than 1,000 elements, and each of the all are active phased array radars. Active phased array radars means convention previously in old time and all a single transmitter to multiple elements. So if the transmitter fails, then radar is not at all operational. So nowadays, all the latest radars, where all over the world is modern active phased array radars. That is, each of the elements are powered with low power transmit receive modules. So even if 17 percentage of the modules are down, your radar will be operational only with a degraded performance. So if you want to make a radar to operate with this many number, you imagine an array which is having more than 3000 elements. You can imagine what is the complexity. So what will happen? We have to send different kinds of signals like digital, analog, and RF to various elements as well as to the TR module for the normal operation of the radar. So what will happen? It will add weight, loss, interference, and complexity of the entire system. And you can see that the backside of the antenna will be looking very complex also. Again, this I have taken from the internet only just to show you how to how to how a radar system will be. So don't think that in a bigger radar system you will have an antenna with a pedestal assembly, and there will be a power system shelter, there will be a cooling system shelter, and there is an operational shelter where the people will be sitting and operating. So you assume that whatever signals has to be distributed here, if we are able to uh, send it through a single fiber from here, and in the that distribution happens in the array, but that means the transmission of the all the signals are happening through a single fiber using WDM link. And if I am giving to antenna, in the antenna I can take the distribution. Here the advantage is instead of having multiple cables, we can use a single cable. And again, do we really require this? Answer is yes, because I told you that different types of signals are required to be taken to the antenna for normal operation of the radar. So if each of the signals are transmitted, I'm sorry, here I think the bullets are getting not shown properly, but still all the points are there luckily. So if I'm having five signals and five cables, if I'm taking the huge that bulky cables, it adds to the weight of the array, and it adds because of the cable weight. And the moment the weight of the array increases, what will happen? If I have to rotate this huge giant here, you require a driving mechanism also accordingly. That means if I have to rotate this antenna for 360-degree, you have to, your drive mechanism also should be high depending upon the weight of this antenna. And another thing is, because of the losses due to RF cable and all, majority of the major subsystems will be residing as part of the antenna itself. So in when we are using photonic solutions, it need not be, majority of the systems can be down, only the antenna can be kept, and all the received signals can be brought down, and similarly all the required signals can be taken up through the fiber cables. So it will reduce the complexity, and it reduces the loss. I told you again, the way loss factor, where RF cables are giving a loss of 1 dB per meter, here it is capable of giving 0.1 dB per kilometer, and it will be free from electromagnetic interference. This is only to show when we were selecting a particular approach, we had to give a thought on different schemes possible. In this, suppose if I have to multiplex five signals, I have to generate five lambdas and then multiplex over a single fiber. And depending upon the splitting requirement, we have to either we can provide an amplifier or without amplifier. Then these signals are converted. Sorry, each of the signals. Suppose you assume that I have to distribute six different signals, sorry, five different signals to six. You assume that each row, I'm having six rows, say. So if you want to give it to, okay, here I have put a slide with the four rows. If I have to distribute here, what exactly I wanted to tell is, in this case, here you don't worry about the number of rows and other things. I wanted to tell you that when you are distributing the signal like this, after splitting, I'm demuxing it and then splitting it. In this method, suppose if you want to give 24 element, one hypothetical array you can imagine, means 24 elements. Each row is having six elements, you assume, and four rows. Sorry. So if you are distributing like this, you will have 1 by 8 splitter, one number you require, 30 numbers of 1 by 8 splitter, and 4 numbers of 1 by 8 demultiplexers for each row. So this is, I just wanted to, you need not worry about this numbers at all. What I wanted to convey is, before designing a particular thing, we should always consider different approaches. Suppose in this method, you can see the difference here. We are doing the first, in the scheme one, what was that? It is demultiplex and then splitted. In this case, it is splitted and then demultiplex. So in this case, you require a splitter of 1 by 32, but 24 numbers of 1 by 8 demultiplexers. In the case of the scheme 3, we are demultiplexing based on the number of signals to be distributed, and based on the total number of modules to be distributed, it is splitted. So you can see that here one demultiplexer and five numbers of splitters, and each one will have, it should have 1:32 outputs or whatever it is. So whenever you are designing a system, you should have multiple options, and we should see not only in terms of the compactness, we should also see the power requirement, then we should also see what is the um, cost. So all these factors should be considered before finalization of a design. So suppose one more option I have pulled out here. There is a hybrid solution. Hybrid means your signal will be multiplex and coming to the antenna, and from the antenna the distribution is happening in the convention RF domain. That means as soon as it reaches the antenna, it is demultiplex, and five signals are separated out, and these five signals are then converted to electrical domain, and in the electrical domain or RF domain, this distribution is happening. So what exactly I wanted to tell you over here is, uh, out of this four schemes, if we take say the second scheme, where we are, the transmitter section will be like this, that is five signals. You assume that these are the five signals to be distributed to the antenna. One is local oscillator signal 1 and local oscillator 2, and the actual radar transmit signal and the clock. And all these signals, here only four are shown. You assume that in the previous case I have taken five. So four signals we have to multiplex, and then 1 minute. Four signals are multiplexed with the help of a optical mux, and then it is passed through a amplifier and given to the antenna. This is only the transmitted portion. Okay. Now the receiver section will be any of that scheme we have in the actual implementation. We went about with the scheme number 2. So before that, I wanted to tell you that you have to do a lot of analysis. We cannot just like that go and accept one method. So what we did was, first we tried to pass RF signal over fiber and see what happens to frequency, what happened to the delay factor, what happens to the phase of the signal. So if you see, we have done multiple experiments with a continuous wave RF signal, pulsed RF, and modulated RF signal. In the case of modulated RF signal, we tried with both LFM and NLFM signals. We also tried to introduce delay by using different fiber spools. We also tried to see what happens to the output signal. So we repeated the experiment with a different length spools, like 150 meter, 500 meter, and 1 kilometer. So I will also share with you some of the results that we obtained. In the case of, I showed you this slide you have seen when I was talking in general about the various micro techniques, not in the case study. You can see that from the transmit section, the signal is converted to optical by using a RF over fiber transmitter. Then further the signal is received and it is converted back to RF with the help of a ROF receiver. And the signal is then monitored with the help of an RTSA and oscilloscope. So the same thing only I am showing here. From an exciter, the signal is converted to optical with the help of RF transmitter. Then it is passed through the fiber and the signal is converted back to RF with the help of RF receiver. And then it is passed to this RTSA as well as the optical oscilloscope for the evaluation purpose. So these are the some of the results which we obtained with a continuous wave signal of 3.1 gigahertz frequency. You can see that this is input and output. There is a difference in the amplitude, and this is the phase variation. And this is with a pulse RF. In the case of pulsed RF signal, also we could maintain we could get the almost same input and output after passing through the fiber link. And this is the envelope of the envelope of the transmit signal, and this is the envelope of the output signal. And in all these things you can see that the signal is getting attenuated anyway. Law of conservation of energy remains same whether you do it in optical domain or electronics domain, it remains same. So energy cannot whatever be the energy, it will be getting dissipated in the form of another one only. So here you can see that this is with NLFM, that is non-linear frequency modulated signal. We have also tested with other modulation schemes also. I have not included all the outputs. So here in the case of one second, it is sorry. So in the case of NLFM signal also, you can see that it is retaining the same shape and the spectrum itself is looking almost having the same shape. And this is the NLFM envelope. I'm just showing you some outputs. And pulse compression, I told you that after getting the RF signal, we can, because the transmit signal we are only generating, so we know the what is the transmit waveform coefficients. So once if we know this transmit waveform coefficients, we can retrieve back the signal after the fiber loop, and then we can do the match filtering process or the pulse compression process. So this is one of the zoomed output of input and output. You can see that there also the signals are maintaining the shape and other things. So this is the this output I had put it in the generic slide, where this green shows the number of pulses and red shows the pulse compressed output. You can see that both input and output are retrieved RF are having almost same, no distortion. Then another experiment what we have done is with the help of different lengths of fiber spool. So 500-meter fiber spool, you can see that one is the input signal and the other one is the output signal, cyan and magenta. And in this case where multiple waveforms, that is not only one pulse, multiple pulses are given. So you can see that there is a delay, and this same thing we repeated. I told you that even RF over fiber measurements with different types of signals we observed with a fixed, when we conducted we observed with a fixed attenuation which we can rectify it. And similarly, when we repeat with a different fiber spool, it is observed that even delays related are basically it is matching with the um, fiber spool length, which can be corrected. So whichever are non-factors, we can easily correct it. So here again, the main point of discussion is before designing or accepting a particular scheme for the realization, we have to do a lot of analysis and see whether it is acceptable based on our application requirement. So next thing is, first is what I was showing was with a simple RF link. Now suppose if I am using a WDM link, The WDM means what? Not only one signal, there are multiple signals. Then like in this case, what I have shown is there one is transmit radar signal, and the another one is this. Here you can see that sync signal. Then give it to in the case of transmit signal, NLFM signal, we have to give it to, this is digital and this is RF. So both the signals, in the case of digital signal, simple DFP laser is enough for converting to optical domain. And here we require, depending upon the frequency, I don't know how many of you are exposed to the term direct modulation and external modulation. You all will agree with me that when the frequency of the signal is increasing because of the chirp effect, we cannot use direct modulation. Then we have to go with modulators with external modulation. So the signal is converted to optical domain by using RF transmitter, and that means this will be assigned with a lambda 1, this will be assigned with a lambda 2, and further these signals are multiplex, and the multiplex output is again demultiplex and converted back again. For this, simple pin diode is used, and RF receiver will be used to convert back to RF signal. So then at the receiver end we can monitor this. So here also the same exciter is used for transmitting the RF signal, and the digital signal was given from a pulse generator here, and then both are multiplex. I don't know whether it is visible, this black small segments are showing the mux and demux configuration, and this same block schematic way it is connected over here and it is monitored. So here also I wanted to tell you that after passing through this circuitry also, we measure the amplitude for different signal. This is with the pulse continuous wave, and this is with the delay measurement with the same setup. And here also, I'm sorry, maybe some shift in this thing has happened. So with this WDM also, what I wanted to say over here is, we could observe same attenuation, similar attenuation in all the test cases. And delay also, we found that you will be wondering how come this much delay. And one thing I wanted to tell you, when we were doing the experiments, we were not using very professional cables, and because of that it is not lab level cables only, so the attenuation was more, but this much will not be there in actual scenario when we use a proper cable system. And now the scheme which I showed you, the scheme 2, in which I was mentioning that you can see that this is the radar exciter say. This is a hypothetical situation where we want to transmit 4 RF signals and 1 sync signal. So all the signals which are coming are converted to optical domain. This RF signals or analog signals are converted to optical domain by using RF transmitters. So one is yellow signal, this is another yellow signal, this is clock signal, this is the transmit signal. Then you please have a look here. All these are converted to different wavelengths. And again, here also the CWDM mux is used. Now you will be wondering what is this CWDM? This is cos WDM mux, where if I told you that there is a technology called through a single fiber we can transmit multiple wavelength. And there is one more terminology is that dense WDM, that is DWDM. When your number of signals are more, you can use DWDM. That means the spacing, basically it is separate. It differs with the spacing between the channels. In the case of CWDM, commonly it is maintained around 20 nanometer, and in the case of dense WDM, it is differing with a 0.2, 0.4, 0.8 nanometer. So the advantage over here is CWDM means the channels are far apart, and DWDM means it is dense, thickly packed, and the channels are, so we have to take care of a lot of other aspects. Temperature should be, the laser temperature should be maintained at the proper level. Otherwise what will happen, the shift of lambda, it should not, there should not be crosstalk between the channels. So each of the signals are converted back to different assigned with a different wavelength, and then multiplex by using CWD mux, and it is passed through an amplifier, optical amplifier. So now conventionally nowadays you all will agree with me. After 1990 onwards, erbium doped fiber amplifiers can be used for the amplification of signals in the 1550 range. So this hello. So this output is splitted and converted a demux to further, and to obtain the original signal we are using a RF receiver. So so what happens here? We should have a WDM transmitter, then one WDM amplifier and splitter unit, and a WDM receiver unit. So this is total optical distribution network where transmitter, amplifier, and splitter receivers are there. And this system, comes,
ಅಸೈನ್ಮೆಂಟ್ ಒನ್ ಆಲ್ರೆಡಿ ಬಿಟ್ಟಿದ್ದಾನೆ
excuse me,
ಮತ್ತೆ
hello. So hello. So the output after converting back to this electrical domain, it can be fed to the arithmetic. So basically, the highlight over here is convert all the signal to optical, mux it in the optical domain, amplify and split it, and convert back to wherever the destination is. Now, the WDM receive module, transmitter module, and amplifier and splitter unit. Now, just to for you to get a feel of this, I've just shown you. This is the transmitter unit, and this is the amplifier and splitter unit, and this is the say 24. If you are taking the resolution as 24, you will have 24 receiver modules. I'm also showing the photograph of this transmit module. Suppose if it is 4 RF receivers, sorry, transmitters, you can see this receiver transmitter modules and mux, and the single output will be coming out of this. And when you are muxing, I wanted to show you that if 5 signals are muxed, 4 RF and 1 digital, then you can see that each one is having separate wavelength, and based on the signal power, it is showing this is the OSA output. OSA is nothing but optical spectrum analyzer, where x-axis will be for the wavelength and the y-axis will be for the power. Now this is the WDM amplifier and splitter unit, in which the basic amplification of the signal will be happening, along with the this is the splitter module for to multiple splitting into, like this is equivalent to our conventional RF splitter. And this is the photograph of a receiver, where the demux is there, and as well as that we have to have that receiver module which will convert from RF to electrical domain. Now, I just wanted to show you, even after making the entire unit for this thing, for such a huge number also, we could get various signals with its own accuracy and accuracy requirements and amplitude requirements. So this corresponds to a signal output for 2.7 gigahertz. And this corresponds to a transmit signal output, which is corresponding to 3.3 gigahertz, and this corresponds to a clock output which corresponds to 50 megahertz. So, and one last but the point, the least point which I want to convey to you is, before I end my talk, is before, when you are trying to design a system with the photonics, you should also, especially when you are using for a defense application, you should always make sure that each of the components which are used in the system should be environmentally, and from the electromagnetic perspective, it should be proof. That means when we tried to realize this, we found that except optical amplifier, all were having very good operating temperature range. But only in the case of amplifier, it was of lesser operating range. So see, the why it is required is one thing I will tell you. Today, if we are using in Leh Ladakh, tomorrow we may have to use it in Rajasthan. So you will agree with me that there is a wide difference of temperature in the environment itself. So in both the places, it should work without having any issues. So whenever we are designing, it is not only the functional requirements should be satisfied, even this qualification requirements also should be considered. Then only in our case, we can tell that a product is fully successful. So I wanted to tell you that in this case, we found that optical amplifier is not having the enough temperature range, and we had to make a separate outer enclosure where the ambient temperature will be remaining same. So with that, we could maintain and the ambient temperature to a fixed value, and we could use all the required uh, we could always we could meet the all the required specifications. So finally we have concluded. I think I am on time. I will leave 5 minutes for the discussion. So I just want to conclude my session by highlighting of a recap of what we have discussed today. Basically, I was trying to explain to you how photonic technologies can be used in defense applications, and then we moved on to specifically to microphotonic application in radars, basically. So we also found out that these techniques can be used for photonic RF signal generation, then distribution and detection, and this includes even optical beamforming also. So all these are immense. I can tell you that the future is actually a lot of photonic units are going to come. And then this I also brought out a case study on WDM based radar signal distribution, where you could also find that we need not keep everything as part of the array. We can keep it as part of the operational shelter itself, and this will bring a reduction in the drive mechanism capacity, which is used for rotating the antenna. I told you that as the weight of the antenna increases, the drive mechanism capacity requirement also is going to increase, and it reduces the overall weight and less loss. So with this remarks, I just wanted to tell you that due to the latest advancements in this microwave technologies, I'm quite sure that combined solution of MWP and the digital will play an important role in enhancing the performance capability of future class of radar system. It is a merging of, it is a combined solution between the MWP and the microwave and digital technologies will provide a better solution for all future class of radars. Thank you for your patience listening. Thank you.
Thank you, ma'am. Thank you for a great session. We are now open for questions, dear participants. You can unmute yourself and ask questions.
Hello.
Hello. Yeah.
Yes, ma'am. Myself, Jnana Kumar from National Institute of Technology, Tiruchirappalli.
Yeah.
I was wondering about your presentation. It's more colorful and more meaningful. It was very interesting, ma'am.
Thank you. Thank you.
Okay, next to come to the question part. Let us start with the basics question. What is the difference between optics and photonics, ma'am?
Optics and photonics, it's a good question actually. Like basically, if you ask me, I told you that like if you see, it's a broader.
Hello? I could say interruptions stop there.
I'm not able to properly. Hello? Hello? Hello?
Yes, ma'am, you're audible, ma'am. Yes, we can hear you.
No, what happened? Lot of distraction.
Yes, ma'am. In between, I think one of the participants was unmuted. So, yeah, sorry for that. Yeah.
Okay. Again, I am talking from the perspective of a classical definition. Optics cover a more broader range of.
I could say in this way, the way of propagation we tell that optics, the way of light wave propagation.
Yes. Right. Hello.
Okay. Yes, ma'am.
Yeah.
Ma'am, next question.
Yeah, please go ahead. Your lot of distraction is there. Yeah. Hello.
Yes, ma'am. Yes, ma'am.
Next question is that you say, hello.
Yes, you're audible.
Hello?
Please go ahead. Yes, you're audible.
You said the photonic assist technology, it's a immunity to EMI, electromagnetic interference. Yes, ma'am?
Yes.
Could you measure in terms of radiation, ma'am, whether it is absorbed?
No. See, this is the basic thing itself. I'm not telling anything because there is no conduction media. The
So,
moment you convert to light, no, there is no
yes.
interference. That is the basic reason.
So I'm talking about the green communication point of view, ma'am.
Okay.
It is health hazards to the human, right? It is hazarded to human. Like in the terms, photonic will provide less hazard to the human body, right? The
Yes.
radiation.
From a photonic system, there will not be radiation because there is no conduction media.
Yeah, yes, ma'am.
Yeah.
Oh, okay. Next question. When we go for higher frequency,
Hmm.
the attenuation take place in free space, right, ma'am?
Attenuation.
Take place in free space when you transmitted millimeter wave frequency in the free space. Due
Okay.
to the weather condition and ambient condition, there will
Yes.
be attenuation take place. How
Yes.
to tackle this challenge, ma'am?
See, that only I wanted to tell you. I'm even in my photonics radar means I told you that the front end will be RF itself.
Yeah,
I'm
yes,
not
ma'am.
talking about lidar. Lidar
Oh,
means the light will be transmitted.
ah,
Okay. So I
okay.
am transmitting only, and we also limit the when we are transmitting the RF frequency, we will consider all these aspects, and accordingly only we will select the frequency of transmission. It is not that we can go up to 40, but what I wanted to highlight was photonics can give even the signals. We can generate even the signals up to millimeter wave with the same architecture. That was the point which I want to highlight.
Okay, okay,
Then,
okay, ma'am. But
like
the transmission waves in terms of not gigahertz.
Lila, in the case of photonics radar, the transmission wave will be in the micro region.
Microwave region.
Yes.
Okay, ma'am. Okay. Thank you, ma'am. Thank you so much.
Yeah. Welcome.
Madam, there's a question in the chat.
Yeah.
So what type of optical fiber is used in radar applications?
Most of the time we are using single mode fibers which can be operate in 1550 range. Did I answer your query?
Yes, madam. It is single clad or double clad?
That is again I am just telling commonly used any rugged type of cables with a single clad itself is more than enough.
Okay, for WDM application, it is also single mode.
No. Here you should not get confused with there. Are you talking about multi-mode communication, or here what I meant was each signal should be converted to uh, each signal should be converted to one lambda. That is achieved through with the help of laser. Nothing to do with the mode can be one, but the wavelength is changed.
Okay.
Okay, there is
Okay.
something called multi-mode propagation, like mode multiplexing technique. I'm talking about wavelength division multiplexing method. Hope I could convey your query properly.
Okay, madam.
Yeah.
Thank you.
Yeah.
Yeah. Hello, ma'am.
Yes, madam.
Yeah.
Yeah, this is Padmini Bhatt from Mangalore.
Yeah.
Ma'am, my question is, if we are using WDM, then should we go for up-down conversion?
Your voice got interrupted. Could you please repeat the question once again?
Yeah, if we are using WDM, then is up conversion and down conversion required?
Up and down conversion is for a different purpose. Do you agree with me? In the conventional radar system, where do we require the up conversion? When we are converting the signal from baseband to RF signal.
RF signal, yes, ma'am.
Similarly, a down conversion we require when we want to convert from RF to baseband signal. Okay.
Yes.
WDM is basically doing only helping us to transmit multiple signals through a single fiber by assigning different. Both are different concept. One is for
Yeah, but
carrying the
no,
signal.
my question is WDM actually we use different high frequency, right? So it is not RF or are you using RF in the WDM? How is it, ma'am?
No, RF means you assume that I am having R1, R2, R3, some three signals are there. Okay. The moment when I convert it to optical domain, it is light.
Okay.
And then it becomes light as lambda 1, lambda 2, lambda 3.
Yes.
Then I am multiplexing.
Yes.
Okay. But
yes.
in the other case, what I am telling is there is both a different concept itself. One is WDM supports for multiplexing of signals for communication through a single fiber. And
Yes.
RF transmitter, that whatever I was showing with optical heterodyne and all, is direct generation of RF signal from the baseband instead of using up conversion and down conversion. Both are different concept.
Okay.
Don't get confused. One is
Yeah.
signal generation and the other one is signal
Transmission, signal
transportation or
transmission.
communication. I hope I could clarify your doubt.
Okay, okay, ma'am.
Okay, RF, you should not, once if I convert that RF transmitter, if I use that RF transmitter at the first stage, it is converted to optical. Once if it is optical, then I'm just, that methodology is used only for transporting one RF to another, or multiple RF with a digital or whatever it is, to another location by using WDM technology. Where I was telling about signal generation and detection is, that is a complete different process for up conversion, and that no up conversion, down conversion is not required in photonic methods. So don't get confused. Maybe if you read much,
Yeah.
you will understand.
Yeah, yeah, it is not required, you are saying, no, ma'am?
Yes. No,
Okay.
required means both are different concept. One is for transporting the signal from one place to another place. I can carry hundreds of signals over a single fiber. The other one, what I told was, suppose if I want to generate directly the RF signal, I can use that photonic transmitter principle. There you don't require up conversion. Similarly, when we are using, suppose if you want to convert RF to baseband, you have to use photonic ADC principle. All are different things, not same.
Okay.
Okay.
Okay, ma'am.
Yeah.
Okay, fine. Thank you, ma'am. Thank you.
Yeah.
Hello, ma'am.
Yeah.
Myself, Dr. Asha Shendge.
Yeah.
I'm from Pune, Raisoni College.
Yes. Please.
Yes, ma'am. I'm currently working on the photonic radar in a Defense Institute of Advanced Technology,
Diet.
DIET,
You're working
under Dr. Basil, sir.
Basil.
With Basil, sir.
Yeah.
So I actually today I get some more idea about this photonics radar because I am basically from electrical engineer.
Okay.
And I want to see this hardware and all these things. So is it can I visit LRD or something, because it will give me more idea about this thing.
Yeah, if you come via diet, something is required, that officially it has to come.
Yeah.
Because all these are evolving fields. So
Yeah.
it's one of the cutting edge technologies which we are working on.
Yeah.
You will also agree with me that I told you that the other part of the world has not at all disclosed. They will disclose after 20 years.
Yes.
Okay, so I also was trying to give only the literature perspective, not the actual products.
Yeah, we have simulated some part in optics CW radar. For that also some mathematical modeling part I want to discuss. So personally, I want to meet you. So that's why I was asking.
Right now, anyway, Basil knows me very well. Okay.
Yeah. Yes.
He knows me.
Sir,
Pardon?
Yes,
No,
sir.
but
Yes.
I don't know right now. Maybe we can take this offline. I will be able to, because
Okay. Thank you,
will,
madam.
yeah,
Thank you, madam.
Any more questions? Okay, looks
I request the participants who are there, can you switch on your video, please, for some time? Meena, madam, you also?
Yeah, I have switched on.
1 minute. 1 minute. One minute. Yes, now you can, I think we can see. Yeah. Yes. Meena ma'am's camera, is it on?
You are not able to see me.
No, no.
I'm able to see you.
Oh, okay.
I'm able to see everybody. Vinia, Asha,
Yeah.
Rajashree, everybody I can see. You are not able to see now?
No, I'm not. You
I
are
think
No,
able to see,
ma'am.
Vidya? Vidya, you can see? No.
you are not able to see.
No.
Oh,
No.
let me see.
I
One
think this sharing screen, you can just remove this one. No?
sharing.
You can stop sharing this one.
Stop sharing. I will do. 1 second. 1 second.